Okay, so the last talk of the second part, the first session of fifth day is by Allison Henrich from Seattle University, and she's going to talk to present a tour of Knotty tricks, games, and puzzles. So it is to you, Allison.
Thank you so much. And it's great to be here. I just want to get a sense for how many people have rope. So I don't know if you want to show me your video or write something in the chat. Just this talk is interactive, and so I'm hoping to interact. Okay, cool. So we have some people with rope. Excellent. Oh, great. And some people with tubes. That'll be interesting. All right. So if you don't have rope, maybe you can perform tricks in your head. That'd be great. So this talk is a talk in 3 acts. We're going to be talking about magic and games and puzzles. So it's all of these wonderful, fun things that you can talk to people who don't know any knot theory about to give them a sense for some questions and theorems that we know about as knot theorists. What did I skip? I skipped this page. This is very important. So a lot of what I'm talking about today is stuff that either Lou has taught me or we've developed together or we've gotten interested in together. So this is all sort of tied up in my connection with Lou, and here we are linked together in Chicago. Okay, so Act 1 is our favorite thing to think about these days, which is magic. And so for this, I'd like you to grab your rope. We're going to learn Lou's favorite magic trick, which is the Chifalo rope trick. So because I'm not sure how well you can see what I'm doing on my video, I have a recording of this trick that I'd like to show you. And this is a very cool trick because what you do is you tie a knot and you make it more complicated. And you make it even more complicated. This is a pretzel knot that's legitimately non-trivial. And you do this threading and everything disappears. So let's learn how to do this trick. So the first step is to tie a trefoil and to tie another trefoil, and you want the second trefoil to be the opposite handedness. So for me, I do right under left and then left under right, and I get something that's opposite handedness. So this is a square knot. And so once you have that square knot, you want to identify the end of the knot that's coming out towards you, and that is going to be your threading end. So here we take this threading end and we're going to thread it down through the bottom trefoil and then down through that big top region, and everything disappears. So try it. So if you have your 2 opposite-handed trefoils, so connect some of 2 trefoils, one on top of the other, you're going to take the strand that's coming out towards you and put it down through the bottom trefoil and down through the top trefoil. I'm doing it backwards, so hopefully you can see it. And everything disappears, which is pretty amazing. For those of you following along at home, I'm just going to play the video one more time in case you need one more guided tour. So 1 trefoil, another trefoil, take the strand that's coming out towards you, down through the bottom, and down through the top to meet the other end. Okay, hopefully you got that. So Lou and I have for years thought that what's important about this trick or what's interesting about the trick is that it contains a persistent tangle. So the square knot that you tie at the very beginning, basically the connect sum of two opposite-handed trefoils, is persistent, meaning that there's no way this tangle can appear inside the diagram of an unknot. So there's no way to connect the four loose ends to each other to basically undo the knotting that's happening inside this tangle. And the way you can prove it is very simple using a tricolorability argument. So you notice this is tricolorable in such a way that all of the exterior boundary points are all colored in the same color. So everything on the outside could be colored red, and that would be a valid tricoloring of your knot. So we thought this was very interesting because how can you unravel something that's persistent? And even when you're doing this trick, once you do the first threading, you have an even more complicated persistent tangle. So what's going on with this trick? Well, when you do that final threading, there's no way to propagate this tricoloring. And it makes sense. Like you have a proof in the rope trick that there's no way to propagate the tricoloring because everything falls apart and becomes completely unknotted. So there's no way to complete this coloring, even if you forget all the colors and you start again. So the key is that we had to thread through the center of this region in the persistent tangle to make it disappear. So we thought that was really interesting. And we wondered if it was essential that the two trefoils have opposite chirality. So this was a question we wondered for quite some time. And I began working with some archaeologists in Scandinavia. And I told them that I was interested in like magic tricks and things like that. We were working on a project having to do with string figures. And one of my collaborators sent me this interesting paper called Ojibwe String Figures and Tricks. And I was just flipping through it and I noticed this picture and I thought, that's the Chifalo rope trick. And then for a second, I thought, wait a minute, they drew it wrong. Because I zeroed in on this picture and I noticed that we had not a square knot tangle, but we have two, like a granny tangle, which is two trefoils of the same handedness. And so sure enough, this trick works. And I created a little video to show you how it works. So here, if we start by tying two of the same kind of trefoil, and we do this thing where we lie the threading end down through the center of everything and pull it up through the bottom left and down through the top right, everything disappears. So if you have your rope, you can follow along. I'll pause it right in the middle. So we start by tying a granny knot. So two of the same trefoils. Now what you're going to do is you're going to take the strand that's coming out towards you and lay it down to create a center line that bisects the knots. So let's see. All right, so you create that center line. Now you're going to come up. So you're going to come up on the side that's opposite from where the top free end is coming out. So for me, it's on the right. So I'm going to come up on the left side and then head down on the right side and everything disappears. Okay, so if you have your rope, hopefully you got that. If not, maybe you can watch the YouTube video later and practice. But so it was very exciting for us to see that we could do a version of the Chifalo trick with the granny knot instead of the square knot. But this key like innovation or this key observation that you can do the trick by lying a strand of the rope down the center line of these two trefoils actually was the key we needed to unlock a generalization of the Chefalo rope trick. So here's a diagram from Lou that he did that's really beautiful, where we can actually stack a bunch of square knots on top of each other. So alternating left-hand trefoil, right-hand trefoil, left-hand trefoil, as many times as you want. And then if you take your threading end and create this line going down the center of your line of knots, then you just go back and forth going down through on the right, on the left, on the right, on the left, on the right, on the left, until you get to the very top and everything will unravel. So that was very cool. We also became aware that Jap Scherfuis, I'm not quite sure if I'm saying that right, he also developed a bunch of generalizations of the Chefalo rope trick, including a similar one to the one we discovered, and also including some generalizations of the granny version of the trick. So this became a big project that we're still interested in thinking about. And here are a couple more variations that we have explored. So we wondered, so we're doing this Chefalo trick always with trefoils. Could we possibly do it with a figure-8 knot? And it turns out that you can. So if you tie a figure-8 knot and tie a trefoil on top, and you thread, so the red end, you thread it down through region 1 and then down through region 2, then that will unknot this knot. And actually, we discovered you could do it with 2 figure-8 knots. So you tie one figure-8 knot on top of another, and they're sort of twisting in different directions. You can also figure out a threading that will undo these two. One of our favorites is a mashup of another trick we really like that we call the false lover's knot. A mashup of that with Chefalo. So there's a trick you can do where you can tie, oh, I tied 2 trefoils that weren't linked. Okay, so you can tie 2 trefoils that are linked together, and you can actually make these disappear by doing a threading. So we discovered that we could make this more complicated in the spirit of Chefalo and come up with another version that undoes. I have a little bit of over twisting in my rope here, but should still work. So if I can see what I'm doing. Okay, so I have my mash up here. I'm going to do a threading. So here I have a very complicated knot. But when I do this final threading, all of the complication melts away. So that's a pretty fun one to practice as well. So there's so much more. There's so many more magic tricks that we've studied and modified, generalized, and even Lou has some gorgeous diagrams of other variations of the Chefalo trick where you wrap around a bunch of times within this lower trefoil to make the diagram much more complicated, and you're still able to make it disappear with one last threading. So there's so much more to talk about here, but I want to shift over now to Act 2, which is games. And this is something that I'm particularly passionate about. And it's something that came up in my very first experience mentoring undergraduates in research. So Colin Adams invited me to lead a research group at the small RU at Williams College. And so I worked with this group of students, Noelle, Sneha, Oliver, and Jen. And what we were doing was we were studying pseudodiagrams, the way that Rohanaki introduced them. And we were trying to develop a theory of virtual pseudodiagrams and also learn about different bounds on knot invariants that you could get from pseudodiagrams. So we were working on this, and one day two of my students came to me and they said, we're trying to do this proof, and in the process, it feels like we're playing a game. So what we're doing is we have this pseudo diagram, and I'm choosing crossing information to try and make it more complicated, and Oliver's choosing crossing information to trivialize it, and it really feels game-like. So we realized it actually is an interesting two-player game, which we call the knotting on knotting game. So here's how it works. You start with 2 players and a knot shadow, and the goal of one player is to make a non-trivial knot. So we call that player the knotter, and the goal of the other player is to make the unknot. So you start with a shadow, but then you start resolving crossings. So choosing crossing information, and players take turns choosing crossing information to try and create either something non-trivial or something unknotted. And gameplay continues until every pre-crossing has been chosen. And once pre-crossing is chosen, it can't be changed. So then the knotter wins if the final diagram is non-trivial, and the unknotter wins if it's trivial. So I'm hoping that I have 2 volunteers who want to show us how this game is played. So wait a minute, can you see? You can't, oh, there we go. Okay, so who wants to play a sample game? And I'll talk you through how to do it if you're interested. I'm going to open up the chat in case people are shy.
Maybe Lou wants to play. How about Lou?
Lou, do you want to play?
Okay.
Sophia, do you want to play with Lou?
Okay. I don't
Okay.
know.
Sophia, do you want to be the knotter or the unknotter?
I want to be the knotter. I think the game is in favor of the knotter.
So,
No.
wait, Lou, do you want to, Lou, you're the unknotter. Do you want to go first or second?
I can go first. Now, how do I make my choice?
So what you do is
I say yellow or green. Is that what those 2 colors are?
yeah, so say a letter and say yellow or green.
Okay, yellow at A.
Yellow at A, okay. All right, Sophia?
Oh, I am the knotter, we said. Okay,
Yeah.
so D, green.
All right. Wonderful. Lou?
B, green.
All right. Good choice. Sophia?
C, yellow.
All right. Seems like you know what you're doing here. Lou?
G, green.
Okay. Sophia?
Oh, I'm sorry. I meant yellow. Sorry.
Okay.
Yeah.
Okay, so H, green.
All right. Lou?
Oh, I'll take a virtual crossing at F. F, yellow.
Okay. And Sophia?
And E, yellow.
All right. Who won?
Looks like Sophia won.
Mm-hmm. Yeah.
Looks
So
knotted to us.
it looks like the figure 8 knot to me, because there are a couple of, you can untwist that F crossing and the A crossing. Is that right?
I think the
Right.
unknotter should be given some partial credit for any untwisting that remains.
Yeah, perhaps. Okay. So let me switch my sharing back to my screen. Okay. So thank you to my wonderful volunteers for demonstrating how to play this game. So this is a fun game because for a number of reasons. First of all, it's a combinatorial game. So given any not shadow and player order, there is a player with a winning strategy. So it's a really fun game to do some research on because you can figure out who has a winning strategy and what it is. So we started off, I always like to start off with twist knots because they're the easiest to get a handle on and the easiest to detect whether you have something that's knotted or unknotted at the end of the game. So my students proved that the knotter has a winning strategy if and only if the number of crossings is even and the knotter plays second on twist knots. And they also studied rational knots with Conway notation that has only even integers. In that case, the second player has a winning strategy regardless of their goal. So some interesting questions that students can explore. So one thing I noticed is that we normally play this game on pseudo diagrams where we start with a shadow and we resolve crossings. But there's an alternative way to play it where you start with just a knot diagram and the moves consist of choosing a crossing and either keeping it the same or changing it. And then once you've chosen a crossing and made that decision, you're stuck with that decision. You can't change it again. So this slight shift in thinking opens up knotting unknotting games for other unknotting operations. And so my favorite unknotting operation was one that was discovered by Ayaka Shimizu in 2010. She proved that this region crossing change move is an unknotting operation. So the region crossing change, you basically choose a region and you look at the boundary of that region and change every crossing on the boundary. And she basically showed that you can do a single crossing change using a collection of region crossing change moves so that it could be used to unknot any knot diagram. So because of this, because there always exists a set of regions so that you can unknot the knot by performing RCC moves, we can play another version of the knotting unknotting game. So for this game, we again start with 2 players with the same goals. And now we start with a knot diagram instead of a pseudo diagram. And in a given turn, players choose a region in the diagram and they can either do a region crossing change or leave it unchanged. But once they've chosen a region, it can't be played again. And so gameplay continues as before, and the goals are the same. So my favorite knot diagrams to play on, as I said, are twist knots. And so here's a sample game. So let's say the unknotter decides to choose one of the twist regions and change it. So that's done some nice things here because it basically unravels the whole bottom part of the twist knot. You can do 2 Reitemeister 2s here, except you're not allowed to do Reitemeister moves mid-game. So you have to keep playing with the same diagram. And so let's say the knotter chooses the region on the left and changes it. So that switches the way the clasp is clasped at the top and it changes one of the twist crossings. So then the unknotter decides to fix this region. Like maybe she notices, there's a Reitemeister 2 move here. I don't want to mess with it. So she attempts to save that region as non-alternating. And the knotter does the same with this alternating twist region. Then the unknotter does this kind of clever move noticing that there is exactly one clasp crossing that's in the boundary of this central region. So she decides to change that, but the Knotter remembered that the exterior region is one that's playable, and that also bounds exactly one of the clasp crossings. So then gameplay continues and nobody really does anything. They just keep the rest of the regions the same. And the Knotter wins because he creates the trefoil. So this is a very fun game to play. I had a group of students who studied this game in an REU that I was leading. And we proved that if you play this game on an alternating twist knot diagram with n crossings, if n is even, the second player always wins if they play according to a winning strategy. And if n is odd, the unknotter can win if playing first. Now, what's kind of interesting is, as far as I know, it's still an open problem to figure out who has a winning strategy if n is odd and the knotter plays first. We weren't able to figure that out in general. So that could be an interesting open problem to play with. So we moved on to some basic torus knot diagrams. We found with the 3-2 version of the torus knot diagram, where you wrap around the torus 3 times this way and around the meridian twice, then the second player has a winning strategy. And then for 2-5, the unknotter always wins if they play according to a strategy. So I love knot games. These are just 2 that I've had an opportunity to study. There are several others that you could study. So Adam Giambrone and Jake Murphy studied the link version of this game called the linking unlinking game, where one player wants to split a 2-component link. And that is a very fun paper where they produce a lot of winning strategies. So my friend Inga Johnson and I also studied this game that I think was suggested to us by Lou, where instead of resolving crossings, we smooth at the crossings, and then one player is trying to create an unknot, and the other player wants to make more than one component. Most recently, I've worked on this really interesting knot game that uses the arc crossing change. So ordinary crossing changes are these 0-dimensional operations, and a region crossing change is kind of like a 2-dimensional operation. So we wondered about what's the 1-dimensional analog, and that would be the arc crossing change, where you have an arc going, from under to under, and you change the crossings at both ends of that arc. So that's an arc crossing change. And we made a game using this operation. And what's really interesting about this game is it behaves totally differently from any other game I've studied, because with every other game, maybe at the beginning of the game, there are 8 available moves, and then someone moves, and there are 7 available moves. Then there are 6 and 5. So it's a very predictable, monotonically decreasing number of moves that's available. But for the arc crossing change game, or the arc unknotting game, you could have 3 available moves and then 1 available move, and then it could jump back up to 2 available moves. So it's a very, very, very slippery game that's much harder to study winning strategies for. But we did discover some winning strategies, so that was very cool. There's another game that basically involves strategically performing Reidemeister moves. And this was written about by Gansel, Meadows, and Ross. And here's a game I was excited to tell you about. So I had a group of students who were working on mosaic knot stuff, and they got really interested in developing this game, which you can actually go to this website, if you get bored during the rest of my talk, you can go play Nottress instead of listening. But this is a really fun game to play that's a lot like Tetris. And you can get bonus points for completing components like link components. You can get bonus points for clearing a bunch of rows at once. But basically, you're trying to make suitably connected rows and columns. So there's so much more. There are at least 3 or 4 other games I've studied that have to do with knotting. So I won't talk more about that, but there's a lot to do, a lot of fun stuff that you can do with knot games. So now I'm going to move on to Act 3, which is puzzles. And the motivating question for me is, how can we puzzleify interesting results in knot theory? And you can start by considering your favorite theorem. So I don't know if any of you know this podcast. It's a very cool podcast called My Favorite Theorem by Kevin Knutson and Evelyn Lamb. And I was able to be a guest on this podcast. And what I said was my favorite theorem was Shimizu's theorem about the region crossing change. So what's very cool about this region crossing change theorem is that they were able to develop this puzzle. Can you see the website? People see this?
Yes, we can see it. Yeah.
Okay, thank you. So they created a website where you can play this kind of lights out game on knot diagrams. And it basically uses, so this one, I guess I'm being very challenged by this. I'm not going to win today. But you can play this lights out game to try and, I guess you're trying to get all the lights on. You're trying to get all the crossings to be pink. But behind the scenes, what's enabling this puzzle to work is Ayaka Shimizu's result. So can you see my slides again? Just making sure. Let's see. Sophia, are you seeing my slides? Just making sure.
Yes, I was nodding my head. Yes, yes.
Oh, okay. Sorry. Oh, I need to unhide you. Okay, so the idea is we make this puzzle by translating this knot theory problem. So a knot theory problem might be, if I look at this 818 diagram, what regions should I change to unknot it? And so I know that I can unknot this diagram by changing these 3 crossings. And so to change those 3 crossings with regions, I would change these 2 regions. And it has the effect of changing just these 3 crossings, since these 2 other crossings are bordering an even number of regions. So that's equivalent to this region select game, where maybe you start with this diagram and you want to make all the lights pink. So then if you select these 2 regions, it will accomplish that. So I love this idea of taking a math result and figuring out how to turn it into a puzzle. So here's another one that Lou brought to my mind, and we have a chapter about this in a book we're writing. If you love spatial graphs, then you probably know about this paper from Conway and Gordon, where they proved that every spatial embedding of K6, the complete graph on 6 vertices, contains a non-trivial link. And so a fun way to turn this result into a puzzle is to ask someone to find 2 linked triangles in the picture. And you could even go further. You could have them create their own embedding of K6 and then challenge them to find 2 linked triangles in the picture. And so I don't know if you want to stare at this. I might give you just a few seconds to look and see if your eyes are drawn to the 2 linked triangles. But perhaps you noticed these two triangles, the red and the blue, are linked together. So that's a fun puzzle, and you can make even more use of the mathematical result by giving this follow-up bonus puzzle. What if we change this crossing here back in the graph? And so these triangles are no longer linked with each other. Now find two triangles that are linked. And you can keep doing this until you start, noticing the same triangles popping up. But this is a very fun puzzle you can give to someone who knows nothing about, the theory of spatial graphs. Okay, so what other linked puzzles can we create? Recently, Lou and I read a paper that featured a result from Brune, which is a result that we're probably all familiar with about Brownian links. So Brownian links are links such that if you remove any one component, you have the unlink, but together all of the components are linked. So the theorem that I'm referring to is just the theorem that says Brownian links exist, from 1892. And a fun way to puzzleify this result comes from Domain and a bunch of collaborators. They studied picture hanging puzzles. So here's the puzzle. Hang a picture on 3 nails such that the picture will fall if any one of the nails is removed. And here is a picture from their paper that just suggests exactly how this relates to Brownian links. So if you start with a Brownian link where you separate 3 of the components to be concentric circles, and then you create a 4th component that has no self-intersections, then you can cut those concentric circles and straighten them out. And if you imagine looking at them from above instead of straight on, then they look like 3 nails. And you can see how that 4th component is winding around the 3 nails to come up with a solution to the picture hanging puzzle. So that's a very clever way of creating a puzzle from a fun math result. So how can you puzzleify your favorite theorem? I'm offering this to you as an invitation. And I don't know, maybe you have to think strategically about what your favorite theorem is for the purposes of this challenge, but I think it's a really fun challenge.
Getting back to Conway-Gordon, you go up
Yes.
one and you have the fact that the K7, the complete graph on 7 vertices, is intrinsically knotted, which means same puzzle, but find the knot in the K7. It's harder.
Yes. Yes, much harder. Yeah, thank you. All right. I went a little bit fast, so I'm done early, but if anyone has any questions or wants to learn more rope tricks, I'm happy to answer questions.